Welcome to today's Explainer. I am so thrilled you're tuning in. Today, we're tackling a truly mind-bending concept. We are going to demystify exactly how artificial intelligence learns to, well, see the Earth from space using radar data. We're going to take some pretty complex physics and deep learning concepts and break them down step by step. So get ready and let's dive right in.
It really all starts with a seemingly impossible question. How do you actually teach a machine to see the world from space? I mean, think about it. We're talking about taking physical realities like deep oceans, dense forests, massive concrete cities, and translating them into something a mathematical neural network can actually understand and learn from. It's a huge challenge, but the solution is absolutely fascinating.
Okay, let's dive into this. The vibrant mosaic you see here is basically our end goal. We want to teach an AI to accurately look at satellite data and automatically classify diverse land covers. We want it to instantly recognize the difference between, say, an annual crop, a thick forest, a bustling highway, and a winding river. But to get a computer to do this automatically, we have to start at the very origin of the data itself. So here's our roadmap for today's Explainer. We'll be looking at seeing Earth differently, how SAR radar works, translating signals to images, the machine learning pipeline, and finally, training and grading AI.
Section 1. Seeing Earth differently. The origin of data. You know, different sensors have completely different ways of perceiving the physical world. A standard camera captures visible light, a thermal sensor feels heat, but radar? Radar does something entirely unique. And as author Hyman Namdari points out right at the start of his book, machine learning does not begin with a model, it begins with data. This is a golden rule. An AI model is only ever as smart as our understanding of its input data. If we don't know what the satellite is actually measuring, our AI is literally flying blind.
All right, Section 2. How SAR radar works, or as I like to call it, the bat in space. Let's look at the actual mechanics of our primary sensor here. SAR stands for Synthetic Aperture Radar. It's an active imaging technology. But honestly, to make this super intuitive, just picture a bat. A bat uses echolocation to navigate, right? It sends out a sound wave and listens for the echo bouncing back off a moth or a cave wall. SAR does the exact same thing, but instead of sound, it uses electromagnetic microwave pulses, and it's doing the whole routine from the vacuum of space. To really grasp why SAR is such a game changer, let's compare it to standard optical cameras, like the one sitting in your smartphone. RGB optical sensors are completely passive. They depend entirely on sunlight to reflect colors back to the lens. So if it's cloudy or if it's nighttime, they're pretty much useless. But SAR is active. It generates and sends out its own microwave signal. This gives SAR a literal superpower. It can see clearly through the heaviest storm clouds and even in pitch black darkness, no sunlight required. Just imagine the journey of that radar pulse. A large transmitted wave leaves the satellite and travels all the way down toward Earth. Then there's a delayed returning echo. Now that echo is delayed in time and it's much weaker in amplitude. Why? Because that energy had to travel all the way down to the Earth's surface, bounce off something like a building or a mountain, and make the incredibly long trip back up to the sensor. Moving on to Section 3, translating signals to images, making sense of the echo. Now, what's really interesting about this slide is seeing how we take those invisible microwave bounces and transform them into a format we can actually analyze. Bright pixels basically mean a strong radar return, while dark pixels mean a weak return. In a real SAR image of the Earth, bright white pixels represent hard, geometric structures like buildings that bounce the radar strongly back to space. Those dark, almost black areas, those are smooth surfaces like a calm lake or a river, which just scatter the radar wave away, leaving practically no echo for the satellite to catch. Actually, scratch that. I want to clear up a major misconception real quick. When you look at a SAR image, you aren't just looking at a simple black and white photograph of the ground. SAR brightness doesn't measure color at all. It measures a really complicated combination of physical factors. It's measuring how rough the surface is, the angles of the structures it hits, how much moisture is in the soil, the electrical properties of the materials, and even the exact angle the radar hit the ground. It is literally physics painted in grayscale.
Okay, Section 4, the machine learning pipeline, pixels to predictions.
We're shifting gears now from the physics of radar hardware up in orbit to the computer science of machine learning down here on Earth. This is your central workflow for applied artificial intelligence in remote sensing. We start with the sensor data, those echoes we just talked about. Then we pre-process that data, meaning we resize and normalize it so the computer doesn't get totally overwhelmed. Next up, we feed it into a CNN model, which acts as our brain, extracting features. And finally, it spits out a prediction, assigning a class label like forest or highway. Let's zoom in on step 2 for a second.
Before our AI can actually learn anything, we absolutely must convert our image into a learning-ready numerical array. In the machine learning world, we call this a tensor. Standard optical images have 3 channels, red, green, and blue. So their tensor shape is 3 by height by width. But a standard SAR image is often just one single channel of backscatter strength. So its tensor is shaped as 1 by height by width. The underlying math literally changes depending on the sensor you're using.
And now for the true brain of our operation, the convolutional neural network, or CNN. Imagine the CNN as a giant magnifying glass slowly scanning over our grid of numbers. Early on in the process, it might just recognize a really simple straight line. But as it scans deeper and deeper, it combines those lines into corners, then into textures, until eventually it recognizes complex spatial patterns and says, aha, that specific texture right there is a dense forest.
Which brings us to section 5, training and grading AI, testing our model.
So we've built the whole pipeline, but how do we actually figure out if our newly trained AI learned anything useful about the Earth? Well, we have to grade it, much like a student taking a class. To do this fairly, we split our data into 3 piles. The training set is basically the textbook the AI studies to learn the material. The validation set is the practice quiz used to tweak its performance along the way. But the testing set, that is the final exam. It's kept completely hidden from the AI until the very end. We grade its accuracy, which is just counting how many correct quiz answers it got. But we also measure loss, which is super fascinating. Loss measures how confident the model was when it got an answer wrong. High confidence in a completely wrong answer? Yeah, that's a huge red flag.
And this brilliantly illustrates exactly where our AI needs to hit the books and study more. It's a confusion matrix. The diagonal boxes show where the AI perfectly matched the true label with its predicted label. But if you look outside that diagonal, the darker squares reveal the AI's specific mistakes. For example, it might occasionally look at a dark, smooth highway and totally confuse it for a dark, smooth river. By identifying these exact mistakes, we know precisely what kind of data to feed it next to help it improve. As we wrap up this data journey, I want to leave you with the author's incredibly powerful final takeaway. Quote, SAR is not just an image. It is a radar measurement transformed into an image-like representation. Applied machine learning begins when we respect that transformation. You can't just throw raw data at an algorithm and expect pure magic. You have to respect the physical origins of the data. We've seen how a single pulse of microwave energy from space can be caught, translated into math, and understood by a neural network to classify the world around us. It's just incredible. So my question for you is, as these models get smarter and our radar gets even sharper, what hidden patterns about our Earth will we uncover next? Thank you so much for joining me on this explainer. Keep exploring, and I'll catch you next time.